A doubly reinforced beam of width 230 mm and 500 mm total depth is reinforced with 4 numbers of 16 mm dia as compression reinforcement and 6 numbers of 20 mm diameter as tension steel at an effective cover of 40 mm on both sides. Find the safe UDL the beam can carry if it is simply supported over an effective span of 5 meter. Use M20 grade concrete and Fe 415 steel. For getting the safe load on the beam, calculate the stress in the compression steel first, then determine the neutral axis depth and compare it with the maximum neutral axis depth. Finally, we calculate the moment of resistance and equate it to maximum bending moment for a UDL acting on the simply supported beam. Let's write the given data first. Width of the doubly reinforced beam. B is equal to 230 mm. Total depth of the beam. Capital D is equal to 500 mm. Compression reinforcement four number of 16 mm dia bar. Area of compression reinforcement that is ASC 4 into 5 by 4 into 16 square. ASC is equal to 804.247 mm square. Tension steel is given as 6 number of 20 mm dia. The area of tension steel is AST is equal to 6 into 5 by 4 20 square. AST is equal to 1884.955 mm square. Effective cover say D dash is equal to 40 mm. Effective cover is the distance from top of the beam to center of compression reinforcement. Similarly, from bottom of the beam to center of the tensile reinforcement, which is given as 40 mm. Therefore, effective depth small d is equal to overall depth capital D minus effective cover 500 mm minus 40 mm 460 mm. And the grade of concrete is given as M20. For M20 grade of concrete, characteristic strength of concrete FCK is equal to 20 Newton per mm square. Grade of steel given as Fe 415. For Fe 415 grade of steel, yield strength of steel Fi is equal to 415 Newton per mm square. Now calculate the stress in the compression steel. For calculating the stress in compression steel, find out the ratio of effective cover to effective depth, that is D dash by D. D dash is 40 mm, effective depth is 460. The ratio comes to 0.0869. Calculate the stress in compression steel based on the D dash by D value. We got d dash by d as 0.0869. For Fy 415 Newton per mm square, d dash by d values from 0.05 to 0.2 are given. Write the d dash by d values for Fy 415 Newton per mm square. 0.05 FSC value is 355 Newton per mm square. For 0.10 it is 353 Newton per mm square. Calculate FSC value for 0.0869. Interpolate it. FSC is equal to minimum value is 353 plus difference between these two, 355 minus 353 divided by difference between these two, maximum minus minimum, 0.1 minus 0.05 into difference between these two, 0.0869 minus 0.05. FSC is equal to stress in compression reinforcement 354.476 Newton per mm square. Now calculate the depth of the neutral axis by equating the total compression force is equal to total tensile force. Total compressive force C is equal to C1 plus C2, where C1 is the compressive force due to the limiting section, C2 is the compressive force due to the imaginary section. Total tensile force T is equal to 0.87 times Fy into AST. C1 plus C2 is equal to T. C1 is equal to 0.36 times FCK into B into XU plus C2 is FSC into ASC. ASC is the area of the compression reinforcement, is equal to 0.87 Fy AST. Substitute the values here. 0.36 20 into B is 230 into XU plus FSC is 354.476 into EASC is 804.247 is equal to 0.87 into 415 into 1884.955. 1656 times XU plus 285,086.25 is equal to 680563. Therefore XU is equal to 680563 minus 285,086.25 divided by 1656. Neutral axis depth XU is equal to 238.814 mm. Now look at the note given in the IS 456 in the page number 70. The limiting values of depth of neutral axis for different grades of steel based on the assumptions in 38.1 are as follows. Fy 250, 415 and 500. XU max by D. For Fy 250, XU max by D value is 0.53. Similarly for other Fys 0.48, 0.46. So in our question the grade of steel is 415. So for Fe 415, XU max by D is equal to 0.48. Therefore XU max is equal to 0.48 times D. We know D is the effective depth of the beam, that is 460 mm. XU max is equal to 220.8 mm. We have calculated neutral axis depth XU is equal to 238.814 mm. Comparing these two values, XU is greater than XU maximum. So it is becoming the over reinforced section. We should have to avoid over reinforced section whenever it is designing a doubly reinforced beam. So XU is limited to XU maximum. Therefore take XU as minimum value of above 2. Therefore XU is equal to 220.8 mm. Now calculate the moment of resistance. MU is equal to, for a doubly reinforced beam, 0.36 times FCK into BXU is the C1 value into D minus 0.42 times XU, plus for the imaginary section part, compressive force is FSC into ASC and lever arm is D minus D dash. MU is equal to 0.36 into 20 into breadth of beam is 230, XU into effective depth is 460 minus 0.42 times XU, 220.8, plus FSC 354.476 into 04.247 into D minus D dash. D is 460, D dash is 40. Therefore moment of resistance is equal to 254.024 into 10 power 6 Newton mm, 254.024 kilonewton meter. Let's assume WU be the safe ultimate load on the beam. Calculate the factored bending moment. Factored bending moment is equal to WU L square by 8. We know the given effective span is 5 meters. Factored bending moment MF is equal to WU into L is 5 meters, L square 5 square by 8. Factored bending moment is equal to 3.125 into WU. Equating this factored bending moment to moment of resistance of the beam, WU is equal to 254.024. Therefore WU is equal to 254.024 by 3.125. WU is equal to 81.287 kilonewton per meter. So this is the ultimate load. So we have to calculate the safe working load. So we know ultimate load W is equal to factor of safety into working load. WU is equal to factor of safety is 1.5 into working load. Say working load WW 81.287 is equal to 1.5 into WW. WW is equal to 81.287 divided by 1.5. WW is equal to 54.12 kilonewton per meter. So it is total load, that is including the self weight. If you want to find out the safe working load excluding the self weight, then we have to calculate self weight of the beam. Self weight of the beam, Ws is equal to unit weight of RCC into volume of the beam. We know unit weight of RCC is 25 kilonewton per meter cube into breadth 0.23 into overall depth 0.5 into 1 meter. Ws is equal to 2.875 kilonewton per meter. Now calculate the total weight of the beam excluding self weight of the beam. So W is equal to WW minus Ws. 54.12 minus 2.875 kilonewton per meter, which is equal to 51.245 kilonewton per meter.